Alright, so in this equation we're able to relate the frequency of any transition, uj in wave numbers, to this expression taking into account distortion. And this is an equation of a straight line, so this means if we rearrange, divide across by j plus 1, this means a plot of nu j over j plus 1 against j plus 1 all squared will give us our distortion coefficient, d from the slope, and our rotational constant b from the intercept. So we have some experimental data here, so we can just show easily how we would work through this. So if I just click to the document camera, so here I have my j values, so if j from transition from j0 to 1, well, the frequency there was 14.630 in wave numbers, and so on. So I can just write in my experimental data. So what we want to do is we want to have a plot of nu j over j plus 1 against j plus 1 squared. So our y value against our x y value against our x value. So we were going to plot nu j over j plus 1 against j plus 1 all squared. So this means we just need to calculate these final values. So we can calculate those pretty straightforward. So we've got, obviously this doesn't change. And what we see is these values decrease as we run up the series. So as the molecule is rotating more and more, distortion is having a greater and greater effect. The bond is lengthening, so therefore the frequency is decreasing. So we've got 14.58 and 14.56. So now I've got my y-axis values. I can plot those against my x-axis values, and the slope of that line will be minus 4d. The intercept will be 2b. So if we switch back to the PowerPoint, you can see I put these values in here, and now all I've got to do is just draw the graph properly, and you see that we've got a straight line equation here where our slope will spit out the value for the distortion coefficient, and the intercept will spit out the value for the rotational constant.